Well, thank you, and thank everyone for coming out to listen to me ramble about a very old computer. The story of the ENIAC, to really understand it, you need to go back in time. So I want you to go back to 1943. I would suggest closing your eyes, but I can't see any of you, so I can't tell if you closed them or not. But if you go back to 1943, World War II is raging. It's been about 18 months since the bombing at Pearl Harbor. The United States has entered the war. U.S. industrial production has converted over to war production. We're producing lots and lots of planes, tanks, ships, guns. And the guns are kind of interesting for us because every time somebody comes up with a new innovation for the barrel of the gun, the projectile, the propellant used, it changes the way in which the projectile flies. And so we have to recalculate a whole set of tables because the flight of that projectile is governed, of course, by differential equations, but we're not expecting the people in the field to use differential equations. Let's face it, most of the people that we have drafted don't really know calculus. But the thing is, if I know that my target is exactly 10,000 yards due east, but I've got some wind going north to south, well, I know I've got to point it a little bit north of east. I've got to figure out the elevation of where I'm going to point it based on the distance and the characteristics of the air. And all that has to be done before we can start using those guns. To do this, the U.S. Army employed a couple of sites with a small army of people doing calculations. These people had the job title computer. Now, as you might guess, all of the young men who had just been studying mathematics had been shipped off to the front. So that left the labor pool for this team to be the young women who had recently studied mathematics. And this group, by the way, also competed with the code-breaking group who was seeking to employ people from the same pool. Now, we had two groups doing this. One was located at Aberdeen, Maryland, and one was located at the University of Pennsylvania. Now, the nature of these calculations is very tedious. You basically are sitting there operating a desktop adding machine over and over and over again for hours on end. So maybe there's a better way to do it. Maybe we can calculate these tables faster. And that's where the ENIAC comes from. In 1943, two people at the university issued a proposal and said, I think we can build a machine that will calculate these tables much, much faster by using vacuum tubes. And the Army said, there's a war on, we don't care if it's practical or if you can actually do it, have some money and try. So they got a 6-month contract to kind of prove the ideas. That evolved into another series of contracts. And finally, the machine was finished after spending about $500,000 on it, and it began operation in late 1945. So it actually missed the war, but it was still a very, very useful and important machine for us. It was important in several ways. One, it was a major national computing resource. Even before it went into operation, there was a committee set up in Washington that would receive requests for time on the ENIAC, and they would decide who could have time, when, and schedule it. The other important thing is this is the machine where we learned how to build and program computers. Whether you call it a computer or not, whether you call it stored program or not, that's not really an important question. What's clear is this is the machine that we really use to learn all of that. So to start off with, this is the ENIAC. This is the famous picture of it that you've probably all seen. As far as I can tell, this was actually issued as part of the initial press release of the machine in 1946 when it was unveiled to the public. In the picture, it's a little hard to tell with this one, but this machine goes back into this room about 32 feet. The back wall of it is about 16 feet long. And you can kind of see the scale of the machine by the people in the picture. Now, one thing you will notice is not present in this picture is any form of textual display. There's no mouse, no keyboard. All of the input and output were with punch cards, and the two units on the right-hand side of that picture are the punch and the reader. I'm going to show you a little bit more detail of the machine as we go on. But this just kind of gives you a little bit of a recap of what I was saying, with two additional important points. First, in 1948, they changed the way the machine operated. Now, the machine itself, as we will see, was originally designed in such a way that to program it, you rewire it. But in 1948, they decided, well, if we can rewire it to solve problems, why don't we wire it to be a CPU? And then we can execute instructions sequentially. And that was deployed in early 1948, and that's the way it ran until it was retired in 55. It's a little bit interesting, by the way, the date. For years, it was thought that it was converted in August of 1948. It's recently been discovered that it was actually April of 1948. Now, the reason that's important is that the Manchester Baby first ran its first stored program in June of 1948. So where we always thought the Baby had run before the ENIAC had done anything in a sequential instruction form, turns out the ENIAC actually had come a few months earlier than the Baby. The other thing I want to highlight is even though the motivation and the justification for the funding of the machine was artillery calculation, it was designed to be a general purpose machine from the very beginning. And they knew they were going to be doing a lot more than just artillery calculations. In fact, the first major calculation done on the machine was atomic bomb design for Los Alamos. And I've mentioned some of the other topics here that ran on the machine. One that I had to cut off for space is supersonic airflow. This machine was used in some of the earliest work designing supersonic aircraft by simulating the airflow over the wings. So this was a very, very significant machine, both in its application and in what we learned from it. Now, the two people that I mentioned who put together this proposal for the Army were these two right here, John Mauchly and J. Presper Eckert. John Mauchly was a physicist at Penn. He had come to Penn and was very interested in a number of kinds of problems that were very difficult computational problems. One of his biggest areas of interest was weather prediction. So if you think today's forecasting of weather is bad, imagine what it was like before there were any computers. Well, that's the kind of problem he wanted to work on. Now, along the time he started to teach at Penn, he also took a course one summer that was taught by Eckert on the subject of electronics. And they really hit it off. These two men were the kind of pairing that is sort of, well, more than the sum of their parts. Mauchly saw where computation was needed. He saw how computational machines needed to be constructed in order to be able to solve the kinds of problems he was interested in. Eckert was an electronics genius. Together, they were able to create a machine that most people didn't think was possible. And so it's their leadership that led to the machine. Now, there are a few other individuals I want to mention in the course of this. On the left, we have Herman Goldstein. He was a captain in the Army, and he kind of served as the liaison between the Army and the project at the university. Arthur Burks in the middle, he was a mathematician at the university and was responsible, his biggest area of responsibility was the design of the multiplier that we'll talk a little bit about later. Now, the guy on the right, probably most people have not heard of. yet I would say he's probably one of the most influential people from the work on the ENIAC. His name is Harry Huskey. He passed away only about a year ago at the age of 101. After the ENIAC project at Penn, and he had some involvement with the follow-on project, the EDVAC, he took a sabbatical and spent a year in England, where he worked at the National Physical Laboratory that was the same place Alan Turing had gone after Bletchley Park. Turing had talked about wanting to create a computer at NPL. Huskey actually initiated the process of building a small pilot machine, and that is the machine known as the Pilot Ace. The machine that, by the way, is currently in the History Museum in London. After coming back from England, Huskey led the development of a machine called the SEAC. Sorry, take that back. He did the SWAC, not the SEAC. The Standards Western Automatic Computer. National Bureau of Standards created 2 computers. He led the development of the one on the West Coast. He also developed a machine for Bendix Corporation called the G15. And then he went to teach at Berkeley. While he was at Berkeley, one of his PhD students was Nicholas Wirth, the creator of Pascal and Modula and Oberon. And one of his master students was Ken Thompson. The same Ken Thompson who partnered with the Dennis Ritchie, after whom this room is named, to develop C in Unix. So as I said, Huskey's influence is extremely deep and broad, and hardly anybody's heard of him. Now, there's a few other people I want to mention, and these come from that group of computers who were hired to do the calculations. As the machine was nearing completion, they took 6 of this group and assigned them to be attached to the ENIAC project. Now, the idea was this: if the kinds of problems people are going to be running on this machine are like the kinds of problems they've just been spending the last year or 2 doing by hand, they will be very comfortable with those kind of problems and being able to help the mathematicians and engineers and physicists put the problems onto the machine and guide the operation of the machine. So the initial plan for their role was more akin to what we think of as an operator than a programmer. The reality is, we didn't quite expect the need for programming the way we understand it today quite yet. And in fulfilling their role, they essentially pioneered the role of programming. Now, the first 3 here, Kay Mauchly, Fran Billis, and Jean Bartik. These, by the way, are their married names. Most of the time they were working on the ENIAC, they had maiden names. Kay Mauchly, you might recognize the Mauchly name. The reason is that she did marry John Mauchly. The next 3, Betty Holberton, Ruth Lichterman, and Marilyn Westkoff, these 6 are often sort of referred to as the ENIAC programmers, or the ENIAC 6. There's actually a nice documentary that's been made about them, as well as a broader one about all of the computers who worked there at World War II. There's a 7th person who I've not been able to find a good picture of that I do want to mention, and that's Adele Goldstein. She was Herman Goldstein's wife, and while she wasn't one of these 6 who had been computers assigned to the ENIAC, she was a mathematician who worked with the project, and she was responsible for writing the primary technical manual. And this is the manual that really describes how the machine works in a way that you need to know to program it. Okay, so here's some of the statistics that people always like to quote about the machine. You saw in the picture it's kind of a horseshoe shape. If you were to stretch it all out, you would have a wall 80 feet long and 8 feet tall. Had about 18,000 vacuum tubes in it. You probably at some point will see a more exact number quoted. The problem with any exact number is that the machine was modified and evolved over time. So exactly when do you pick the count of the tubes? So I just said about 18,000. had a 100 kilohertz basic clock. To put that in perspective, that is 10,000 times slower than a 1 gigahertz clock. Now, that clock took 20 cycles to carry out an operation. So while the period of the clock is 10 microseconds, the basic operation time was 200 microseconds. Well, if you invert that, of course, you get 5,000 operations a second. That's where you frequently hear the quote that it could do 5,000 additions per second. But as we'll see, it's actually a much more parallel machine than most people think. And so you could really do quite a bit more than just that. The power draw was about 150 kilowatts. Something in the neighborhood of 50 to 100 houses worth of power. Now, I'm pretty sure the stories are apocryphal, but back when I first joined the faculty at Drexel, people would tell me stories that the lights in Philadelphia would dim when they turned on the machine. Now, if you're like me and grew up in the world of 5-volt TTL electronics, these next two lines are kind of scary. 29 distinct power supplies producing 78 distinct voltages. And most of those voltages were in the several hundred volt range. Yeah, this is not the kind of machine you want to be careful about, just stick your hand in without watching what you're doing. Now, the basic architecture of the machine, this is kind of a rundown of the units. I'm not going to go through and read that off. Instead, what I'm going to do is kind of show you what's contained in the machine in terms of pictures. Now, the diagram that is right here comes from the technical manuals. This is a top view of the machine as it was configured at the Moore School in Pennsylvania before it got moved to Aberdeen, Maryland. They actually changed the layout slightly when they moved it. Now, the view of the overall machine looks kind of like this. And again, those sides are 32 feet long and the back is 16 feet long. Now, starting on the left, kind of going around, we begin with something called the initiating unit, then we have the cycling unit. That's kind of neat because it's got an oscilloscope. You can select which of the clock signals you want to look at and see how, if it's clocking correctly. The next pair of units are the master programmer. The next pair after that are the function table electronics. Now, I don't have it in these images here, but if you remember back to that first picture of it I showed you, there were 3 instances, one quite close to the foreground, where you had a person standing in front of a panel, and he was turning rotary switches. Those panels were where you would put function tables. If you needed sines, cosines, logarithms, that's where you would put that information. So the electronics that sits behind that panel is those 2 there. Then the last 2 in this picture are 2 of the accumulators, where most of the computation is done. In this view, everything's an accumulator except the leftmost unit, which is the divider square rooter. You could not only do division, you could do square roots. And they took about the same amount of time. It was kind of interesting. This is the set of units along the back wall. All but the 3 that are obviously different are accumulators. Those other 3 are the high-speed multiplier. And we'll talk a little bit about that. High speed in this case meaning hundreds of multiplications a second. And that, by the way, was the statistic that really caught John von Neumann's attention. If we have time, I'll tell you a little bit more about that. The next batch is more accumulators and function tables. Finally, the last 2 accumulators, and then these last 6 panels are the interfaces to the card punch and the card reader. They were referred to as the constant transmitter, that was connected to the card reader, and the printer, but there was no actual printer. It was a punch. However, at Aberdeen, they had a room next to it that had a full suite of punch card processing equipment. So when you wanted to print out your results, you would take your cards, carry them next door, and print it out on the printer there. Now, It's not a machine like most of us are used to. For one thing, there's no bulk writable memory. The only available storage you had that was modifiable were the accumulators, and there were 20 of those. So put yourself into a mindset where when you're writing your code, you've got 20 variables to work with. That's it. Well, okay. If you really want only 5 digits each, you could pack 2 of them into an accumulator. So there wasn't really any separation between memory and storage the way we think of our typical CPU memory today. The divider square rooter was a little bit on the approximate side. That is, the least significant digit wasn't always exactly correct. As I mentioned, the machine was very parallel. I love this quote from Lemmer. Lemmer is a mathematician who did a number theoretic project on the machine in the summer of '46. It was oriented around prime numbers. And he actually tested the prime numbers in parallel. He did a sieve Eratosthenes in parallel, testing divisors. So he wasn't too happy when they switched over to the sequential instruction mode of operation. So as he put it, von Neumann spoiled it. As I said, initially we program it with switches and wires. And if you date back to the 80s, you may remember a lot of discussion about data flow architectures. Programming the ENIAC feels a lot like working with a data flow architecture. I've already mentioned the cycling unit that generates the clocks, and that you had the nice oscilloscope for. One of the neat things about it is summed up at the bottom here, these 3 clocking modes: continuous, 1 add time, and 1 pulse. Now, to understand that, let me show you what the clocking signals looked like. Each of the traces in this diagram is one of the different clocking signals that was output by the cycling unit. The top trace, you'll notice, only has 1 pulse all by its lonesome over there in time slot 17. There's 20 time slots here. That's one of those addition times. And that first trace is what's called the central programming pulse. This is the heartbeat of the machine. Every operation is initiated by one of these pulses. Most of the rest of the pulses are actually used to move data around, to construct numbers. For example, if you'll notice, there's a line, you may or may not be able to read it, labeled 1P, then there's 2P, 2'P, and 4P. Those 4 signals allow you to construct any number from 1 to 9. For example, to get 5, I could enable the 1P and the 4P. And a lot of the internals operated that way. Now, the 10P and 9P lines, we're going to look at in a little bit more detail in just a minute. But when the clocking was set up in the continuous mode, this would be free running. You would see this sequence happening 5,000 times a second. If you switched it to the 1 add time mode, then you had a button you could push, and that button would do 1 of these screens worth of clocking. And if you switched it to the 1 pulse time mode, it would give 1 of those 20 time slots. So they had planned for single-step debugging at the very beginning. And this picture is of a portable control unit that would allow them to walk around the machine and do that. Now, this is the only photograph I've been able to find that shows any detail. There are a couple of other photographs where you can tell it's there if you know what to look for. This is my approximation of it on my 3D printer. Now, I will tell you right off the bat that as I was exhibiting this at another event a few months ago, I was glancing at the drawings and realized the cable doesn't come out the top, it's supposed to come out the bottom. Other than that, this works. Now, this doesn't plug into a real ENIAC, it plugs into a Raspberry Pi, but basically this is how you could control the machine. This toggle switch would select the 3 different clocking modes, and then you had buttons for clearing the machine, initiating a computation, reading a card, or the single stepping. And so you had single stepping with 2 different granularities of single stepping. The exhibit I'm going to have upstairs, I'll have this hooked up so that you're welcome to come by and control an ENIAC yourself if you'd like. Okay, so now let's get a little bit more technical. Talk a little bit about how the accumulators actually work. First of all, it was a decimal machine. Everything was done in base 10. Now, the initial idea was this. What we want to do is sort of effectively lash up a bunch of these adding machines like people are using and have them operate collectively. But instead of using wheels that turn, we're going to use ring counters. And each one of those will represent one digit. So each accumulator had 10 digits and a sign. You might think, aha, sign magnitude. Nope. They have a sign and tens complement. A little bit confusing to our modern eye, but it actually works pretty well. You had 5 possible inputs named by the first 5 letters of the Greek alphabet, 2 outputs, A and S. I'll talk a little bit more about those in a minute, but the idea behind those is if I want to add something, I'll send it out the A port. If I want to subtract it, I'll send it out the S port. And each of these had 12 sets of settings that were referred to as programs. To our mind, it's more like an instruction. And essentially what the operation could be is inputting on one of the 5 inputs, in which case you would add what's coming in on that input to the current value, output on A or S or both. There's the 0 for no op. You might wonder, why is there a no op? You'll see. Depending on time. There's what they call a clear correct switch that don't have a whole lot of time to go into it, but it clears after transmitting, adds an extra 1 on input for handling tens complement, and you had a repeat mechanism on most of the programs. So let's say I had X in one accumulator, and I wanted to add 3X to the next accumulator. Well, what I would do is I would activate a program on the first one that transmitted 3 times. And then I would activate a program on the second one that received 3 times. So all your small integer constants in the polynomials were handled directly by this. You didn't have to go to the multiplier for them. Now, the idea of the ring counters is well understood at this point. You basically create a series of 10 flip-flops, you arrange them in a circle, every pulse moves to the next flip-flop, and when you cross from 9 back to 0, you set a carry that goes over into the next one. And these were used quite a lot in devices like counters that were used in radiation research. So Eckert was quite familiar with these. But here's the interesting question. How do you get the data out? You see, for just an ordinary counter, you're expecting a human to read it off. You're sending pulses in to put data there, but how do you get the data out? Well, this is one of the more clever aspects of the machine, I think. And I'm going to talk about exactly how it works in just a minute. But first, that's 1 digit. It was built very modularly. This was part of Eckert's genius in how he built it. But 1 digit's worth of electronics was in one of these trays. It's probably not too far from life size on that screen. It's about 3 to 4 feet long. And as you can tell, it's got about 20 tubes on it. And there were 10 of these per accumulator. And as I said, 20 accumulators. So there were 200 of these digits that were just the data being operated on, not to mention similar structures for control and counting repeats and so on. Now, within that unit then, if I want to read the data out, how do I do it? Well, remember I've got the A output and the S output. A is where I want to do things additively, S is what I want to do subtractively. So what I would really want to do is I want to send the data value out the A, and I want to send the 9's complement out the S. Another way to think of that is I've got a total of 9 pulses I want to send. I want to send some of them out the A and some of them out the S. Well, that turns out to be what those two lines that I said I'd come back to are all about. The first of those that you see on the bottom here has 10 pulses. That causes the counters to wrap around back to where they started. So when you're reading data out, you essentially give every digit 10 pulses. It goes all the way back around to where it started. Now, in between each pair of those 10, there's another one, total of 9, and we're going to route some of them out the S and some of them out the A. And the cleverness is, all we have to do is use the carry to select which. When we start sending the pulses, we start sending them out the S, and then as soon as the carry gets set, we flip that switch and the rest of them go out the A. And the effect is, we've sent the data value out the A port and the 9's complement out the S port. And that's how we transfer data to another unit and carry out the actual arithmetic. And this is really kind of the central core of how this machine worked. Now, I'm going to illustrate it for you here in this simulator of the machine. Now, first thing I'll tell you is that this is not an actual photograph of the machine. This is constructed from many photographs. I went through a lot of photographs, slicing out the best pieces of each one I could find, correcting for any proportion distortion, and then built a ray tracer to image the overall views of it. So that's where these images come from. Now, what I'm going to be doing, remember in this image we have the divider square rooter, then we have some accumulators. I'm going to be using the first 3 of those accumulators. Now, the first thing I'm going to do is load a value into the first one. And if you look closely, some of the lights on that first one changed. The rightmost column now has the light moved up to the position 5, and the next one over to the position 1. This is showing the number 15. Now, I've loaded the number 27 now into the other 2 accumulators. So what I'm going to do is I'm going to read out the value from the 15, I'm going to add it to one of them and subtract it from the other. So to do that, I'm going to switch the mode to the pulse mode so you can watch it happening one step at a time. And as I'm doing it, you will see all of the values in the first one moving up as they roll around to their starting point. Until a carry is set, they go to the third one. Once the carry is set, in whatever column that is, the pulses will go to the second one. And the net effect now, okay, I'm almost done. I've got all of the data read out of the first one. I've got things added up into the second one. I've got some carries to deal with. So we'll deal with the carries. And now we have the results. The second accumulator has the value 42. That was the sum of 27 and 15. And the third one has the value 12, which is their difference. So here we've done a little bit of parallelism in this illustration where we did an addition and a subtraction simultaneously. So that's kind of the core of how it works. I'll have this example at the table if you want to come by and actually step through it yourself and look at how things work. Briefly, I want to say a few words also about the multiplier. Basically, it was all built around multiplication tables, just like what you learned in the second grade. So there's this table that understands all the multiples of, say, 4. It understands that 1 times 4 is 4, 2 is 8, 12, 16, so on. Now, those are separated into their tens digit and their ones digit. So as this operates, what it does is it takes a digit, multiplies it by the whole multiplicand, says, now, let me add up the tens digits, let me add up the ones digits. When I get done with the whole thing, I'll add those together, and that'll give me the product. I'm not going to get into all of the details of how it does it, but if you take a look at these slides, and I'll have them posted for you later, there's an example that kind of works out exactly how that happens one step at a time. Now, the master programmer is really where this machine became quite unique relative to its contemporaries. A lot of people had thought in terms of, let me build something that can crunch a lot of additions and subtractions and multiplications. But in the ENIAC, they knew they needed repetition. And they knew they needed to be able to control that repetition. And that was the role of the master programmer. Essentially, what you had was a set of 6 structures. Sorry, take that back. 10 structures, each of which had 6 stages. And each of those 6 stages could be a loop. So you could actually have fairly complex nested loop structures if you wanted. To make it even more interesting, you could feed data into the master programmer, and as a result, actually have it make a logical decision. And we're not going to have time, so I won't run through the example of it here, but if you want to come by the table, I can show you an example of a case where it actually takes 2 numbers, compares them, and decides which is the greater. And this was something that the ENIAC had, that it could do, that you really didn't see in other machines. The Harvard Mark I, for example, had the same sort of addition structure. It had a special multiplier. It had the idea of function tables. It had a sort of idea of loops, where literally they took the stock of the punch card, wrapped it around into a loop, and that was a loop. But it didn't really have a way of conditional branching. And that's what made the ENIAC so unique. I mentioned the programming. I'll just show you quickly what this programming looks like. When you go to program ENIAC, you do it with diagrams. You don't have a sequential list of operations. Instead, what we're doing is saying, how do the signals go from one place to another? The lines across the top are data trunks. Each of those is 11 cables in this tray, and these are the ones right here in this diagram. These connectors have 12 positions, so you've got the 11 and a ground. The connections down here are for control signals, and each of the 11 signals there is individually accessible, and those are what we have drawn on the bottom of the figure. So what happens is, when we're looking at a control pulse that, say, for example, comes out of, in this case, the initiating operation, then it will travel and trigger an operation here on the master programmer. And when it's done, it triggers something on the next stage, and so on. So let's look at that last one. This bottom control line here, the output feeding it is coming from the master programmer. So it says, I want to do an operation. Now, the particular operation is going to be calculating the square of a number. And it's going to do it using our favorite little equation that n plus 1 squared is n squared plus 2n plus 1. So if I've already got n squared, I want to add 2n, and I want to add 1. So this is, the first step is going to add that 2n. And you'll notice what's happening here. This control line right here is going to correspond to this output operation A. So it says this accumulator's value is going to be transmitted over here, and it's going to transmit 2 times. That same control signal causes this one to read it 2 times. And then when it's finished, it sends this output control signal to start the next step, which is the add 1. So that's the way you think about programming the ENIAC. Just to give you a little sense of what's more involved, this is that maximum one that I was talking about. Doing the, taking 2 numbers, subtracting them, and basically making a decision based on whether the result of that subtraction is negative or non-negative. And the interesting thing is that we can pull out the sign of the number and then feed it in as a control signal. That turns out to be the central mechanism that we use for the more complex kinds of programming on the ENIAC. Okay. So as I said, the programming, the way we've been talking about, is the way it was done before 1948. In 1948, several things have been going on. Now, I'm going to back up to start that story in 1944. The ENIAC project is well underway by now. Eckert and Mauchly are already starting to think about their next machine, the one that's called the EDVAC. Now, at the same time, John von Neumann is very deeply involved with the Army and computational problems, especially in terms of assisting Los Alamos. So one day on the train platform in Aberdeen, Hermann Goldstein sees John von Neumann and goes up and introduces himself and starts talking about this machine. And von Neumann is just kind of nodding along, not paying a whole lot of attention, until Goldstein says, yeah, and we can do 5,000 additions a second and several hundred multiplications a second. And that got von Neumann's attention, because he knew nothing else he had been working with could compute that fast. So he got really interested in the project. Well, it ended up being August of 1944 before he got his clearances to go see ENIAC. Yeah, because of compartmentalization, this guy who was doing stuff with the atomic bombs couldn't go see the ENIAC until he had clearances. So anyway, he comes in and kind of joins the project. Well, by this time, Eckert and Mauchly have already been doing a lot of thinking about the design of the EDVAC. And they've already been thinking about the idea of memory. In fact, in January of 1944, Eckert had written a small paper about a way of doing memory that essentially amounts to magnetic disks. And he had a little sentence in there that said, oh, and the sequence of operations could be stored on this. Now, when von Neumann gets there, he realizes, and to some extent I'm going to be reading into it what I believe happened, because von Neumann knew Alan Turing. Remember, von Neumann was at the Institute for Advanced Studies at Princeton. Turing did his PhD at Princeton. So von Neumann knew him. He knew of the results in the uncomputable numbers paper. And I believe that von Neumann saw what Eckert and Mauchly were talking about and realized, if we do it right, this could be that universal machine from the uncomputable numbers paper. So you will see everybody who talks about von Neumann's involvement will talk about his focus on the instruction set. I'm pretty sure that's why. So anyway, he is consulting with the EDVAC project. In time, Eckert and Mauchly leave the university. Essentially, it boils down to a patent dispute. I'll have to tell you the story later if you want to come upstairs and see it. But basically, they leave the university. Von Neumann goes off to the IAS to create a new machine. And in the process of doing so, he says, you know what, I bet we can convert the ENIAC to be like a stored program machine. And that sort of impetus, where I think he also used it as a test bed for ideas, is what led to that conversion in 1948. And as I said, that's the way it ran until the end of its life. One last thing that was done to the machine is there was a memory added to it. In 1953, they bought a memory unit of core memory, and we now had 100 memory locations. Clearly, our memory problems are over. I mean, let's face it, you only need 100, right? I mean, that's what Babbage said, 64 squares on a chessboard. That leaves you 36 variables to calculate the next move. Surely that's enough. So anyway, that was basically the ENIAC until, as I said, it got retired in 1955. In the meantime, this space, by the way, where it was put, was one of the few places in the area that had air conditioning. So a number of people moved their desks in and started using it as an office toward the end of its life. By the clock I have sitting in front of me, we have 1 minute for a question. And I can't see anybody, so.
Grace Hopper.
Grace Hopper. Okay, Grace Hopper fits into the picture as a little bit of a side thing. When I said that Eckert and Mauchly left the university, they went and started another company called the Eckert-Mauchly Computer Corporation. One of their early employees was Grace Hopper, who had worked for Aiken at Harvard on the Harvard Mark I and the Mark II. So she joined Eckert-Mauchly Computer Corporation working as a programmer on the UNIVAC machines. And it was while she was there that she sort of pioneered the ideas that we think of as compilers today. And of course, then she went on to have her famous talks that she would give where she would pass out her famous nanoseconds. And those prized possession nanoseconds, of course, are in people's wills now. I unfortunately never got a nanosecond from her. If somebody'd like to give me one, I'll take it. The last thing I'll say is that the parts of the ENIAC today are scattered quite widely. But there are those of us who believe the right thing to do is to return it all to Philadelphia, restore it to running condition, and put it on display. If you'd like to help out with that, especially financially, come see me. Thank you.